Phys 1 Kids, Campbell here. In our first video on waves, we're going to talk about some definitions, some terms of what waves are, what the types of waves are, things that affect wave speed. So what is a wave? Well, a wave is just simply a disturbance in a medium that travels outward. Like you drop a stone in a lake, right? You generate waves. When there's wind on the ocean, you get nice big waves if it's really windy. The cool thing about waves, though, is if you think about what's happening with a wave, we're transferring energy by the vibration of the medium that the wave is traveling in, but the medium itself is not traveling with the wave. So you can think of it like this. Say you and your friend are holding a string, and you send a wave pulse down to your friend. We're actually going to do this with slinkies. When you send a wave pulse down to your friend, and the pulse moves, right, it's oscillating up and down as it travels, the wave travels towards your friend, but the rope isn't going towards your friend, right? You're still holding on to it, unless you let go of it. But still, it's not going to go to your friend. So waves are cool because it's a way to transfer energy without transferring the medium itself. Now, there are two types of waves. One is a transverse wave. I call these the wavy waves. So transverse waves, what happens is the medium is oscillating up and down, so perpendicular to the direction of the wave motion. So the medium goes this way, the wave goes that way. Some great examples of transverse waves are things like electromagnetic waves. Those are light rays. Light waves from the sun, from your light bulbs. Those are waves, and what's actually kind of cool about them is they don't actually require a medium to move. Another example of a transverse wave is if you play guitar or the violin, you are generating waves on the strings, and those are also transverse waves. Earthquake S waves, another example of a transverse wave. The other type of wave is called a longitudinal wave. A longitudinal wave, the molecules are actually vibrating in the direction that the wave is moving. Some good examples of that is sound. Sound is actually vibrating molecules, air molecules, and it's causing them to compress and come apart. So that's actually called a rarefaction. Some great examples of longitudinal waves, of course, are sound and earthquake P waves. So these waves move like that. In fact, let's take a look at two different types of waves using a slinky.
Transverse wave, the medium oscillates perpendicular to the direction of wave motion. Notice how the wave reflects when it reaches the end of the bench. Notice that it comes back inverted or on the opposite side of the bench. We're going to talk about that at the end of this video. In a longitudinal wave, the wave medium oscillates in the same direction as the wave motion.
Now, the cool thing about wave speed is that it depends only on the medium carrying the wave. It doesn't matter how big that pulse is that you send down, the shape of the wave pulse, how the pulse was generated, how far it's going, in provided there's no friction present. But it's dependent on really kind of the elasticity of the medium that's in. If we look at waves on a string, the speed of a wave equation is equal to the square root of the force of tension, so that's how tight the string is, divided by this thing called mu. Now, what mu is, move my face again here, mu is the linear density of the string. So it's the amount of mass, it's like a density, it's the mass per length. So how dense that string is, how thick that string is. So the speed of a wave in meters per second is the tension in the string divided by the linear density. Let's take a look at one type of problem. So here I have a 5-gram section of string. It has a length of 2 meters. I don't know why that's a capital M. It looks like molarity. From the wall to the top of the pulley. A 200-gram mass hangs at the end. What is the speed of the wave on the string? Well, first of all, we got to pay attention to units, because remember that in physics we use kilograms. Our wave speed is the square root of the force of tension over the linear density. Now, the linear density we can easily calculate, right? We convert that 5 grams into kilograms, we divide by its length of 2 meters, and we get our linear density. But what's the force of tension? Well, if we drew a free body diagram, the tension is coming from that mass that's hanging over the end, right? And the mass is at rest, which means that the force of tension is equal to the weight of the mass, mg. So we put it in kilograms, multiply by g, and we get that the force of tension is 1.96 newtons. And then we can plug this in to our linear density. Now notice instead of calculating linear density first, I just put linear density and then I did the mass, right? It would be mass over length, but a denominator goes into the numerator. So a little math. Or just calculate the linear density. But you would find out that that's 28 meters per second. Now notice that as the tension force goes up, the speed will go up. So the tighter a string is, the faster that wave's going to propagate. But the thicker it is, right, the more dense it is, then it's going to move slower. So it's kind of like inertia, right, preventing the motion of the wave on, in this case, the string. Let's talk a little bit about sinusoidal waves. So if a source oscillates in simple harmonic motion, which was the last unit we talked about, we get this nice, well, in this case, it's a cosine wave. Now, a couple definition things, right? The amplitude, just like it was with springs, right? The amplitude is the distance from this x-axis to either here or here, but not this whole length. This is not the amplitude. The amplitude is only that from zero, measured from zero. The wavelength is the distance between any two adjacent points. So either crest to crest, trough to trough, or we could even go from here over to here. So the wavelength, it's symbolized by a lambda, and it's just the distance between two identical points. The period of a wave, remember we talked about period is the time for one complete cycle, whether we're talking about springs or pendulums or going around a circle. So same thing with a wave. The period of a wave is the time for it to move one complete cycle, which would be one wavelength. Frequency, remember, is the inverse of period, so we would talk about it in terms of the number of waves per second. Now, remember that wave speed is controlled by the medium, but we can think of wave speed, right, speed being distance over time, the distance being a wavelength traveled in one period. And if the distance is a wavelength and period is the time to move one wavelength, we get our speed, and period is the inverse of frequency, we can derive this equation that the speed of a wave is the frequency times the wavelength. I like to call this the velocity is for lambda equation, and it's one of the given equations on your equation sheet. The last thing I want to talk about is reflections of waves. When you send a wave pulse down a string, down your slinky, down anything, when it hits a boundary, it's going to reflect. How it reflects, though, depends upon the type of boundary it hits. The other thing about it, which you can't see because I'm in the way, is that reflected pulse has an amplitude that's not changed. Now, when the wave is reflected, the amplitude's not changed because that's a reflection of the energy of the wave. And we're not losing energy in that reflection. Well, okay, maybe we're losing a little because friction is the way of life here on Earth. But the amplitude in physics fantasyland doesn't change. But if the boundary is fixed, like here, like the string is tied to a wall, then if it's unable to move or more dense, harder to move, then when the pulse comes back, it inverts. Remember in the video I showed you with the slinky? Notice how it came back on the other side? Well, that's because the end was fixed. So anytime I hit a denser medium or fixed medium, I invert. I come back on the other side. However, if that end is free to move or less dense, when I send a pulse down to the end, it pulls up that end and it will come back on the same side. So we say that it is reflected upright. So here's my wave pulse. My end is free to move, so it lifts up, and when my wave reflects, amplitude stays unchanged, the energy is the same, but it stays upright. So fixed or more dense, it inverts. Free to move, less dense, it stays upright. But the energy doesn't change because we live in physics fantasyland. Now, another way we can do this whole reflection thing is if we are moving to a medium that has a different density. So if I have a light string tied to a heavy string, the wave encounters, as I send the pulse through this light string, when it hits this heavy string, it's hitting a boundary. So some of it, of course, is going to be transmitted through, and it's going to stay in the same orientation. But some of it is going to reflect. Anytime I hit a medium of different density, some of the wave gets reflected. So here is my reflected pulse, and notice because it's more dense here in this string, the reflected pulse is inverted. The transmitted pulse, though, always stays upright, always stays in the same orientation. Now, in the denser medium, right, denser means it's harder to move, the wave speed is going to be less, right? Speed is set by the medium. So if the medium's harder to move, the wave speed is less. And if the wave speed is less, then the wavelength is actually going to be shorter. So notice how this is a more compressed pulse than the original pulse was. We can do the same thing in reverse. If we send a wave pulse down a heavy string, a more dense string, and we have that tied to a light string, what's going to happen now is like I'm hitting a medium that's free to move. Of course, it has a different density, which means I get reflection. Anytime you hit a boundary that has a different density, you get a reflected pulse, but you also get a transmitted pulse. And notice the transmitted pulse is always upright. It's always in the same orientation as the pulse that hit that boundary. But I get a reflected pulse that is upright. It is upright because it is hitting a medium that's less dense. So it moves up and then it comes back on the same side. Now, in here, in my lighter string, it's easier to move, which means the speed is going to increase. That density goes down. I have less inertia, so my speed goes up. And because my speed goes up, my wavelength will increase because speed and wavelength are directly proportional to each other. So if one goes up, the other goes up. If one goes down, the other goes down. Because guess what? Frequency doesn't change. All right, we're going to talk more about that in class. So do your WSQ, and I'll see you in class.